from Breakthrough Listen. But to do that, I also have to give you a little bit of background because Breakthrough Listen is an important project for me personally, even. So before we start the talk, I'm going to share something that I haven't told a whole lot of people about. I'm in astronomy in part because I'm a nerd who always wanted to go searching for little green men. So this is my SETI at home stats from when I was in high school, and had a 133 megahertz Pentium chip with which to process SETI at home data. And my rank has fallen somewhat, but I was in fact 76th in all of India. Considering that we have 1.3 billion people, that's a fairly significant number. SETI at home has, of course, become the Breakthrough Listen project. And today we're going to be hearing about Breakthrough Listen and technosignatures with LSST. And of course, I think we can all agree that if we find intelligent life beyond our solar system, that would absolutely be the biggest boom of all. From slide 0. Somewhere there is a mouse. Oops. It's too well hidden. Ta-da! So, James Davenport from the University of Washington, please tell us about all the cool stuff that you folks are doing.
Well, you made it a lot higher on SETI at home than I did. But I have a similar origin story where in high school, running SETI at home on any computer I could find, any of my relatives that I could hijack their computer and put SETI at home on. So it's nice to talk to you all today about technosignature opportunities with LSST. As Gotham said, I am from the University of Washington. I'm the Associate Director of the Dirac Institute, which does a lot of LSST and Rubin-related things. But today I'm wearing a different hat in my collaborations with the Breakthrough Listen and the Berkeley SETI Research Center group. Two of my colleagues from that group are here today, Vishal Gajar and John Huang. So if you want to talk more about SETI and radio astronomy, they are actually far more knowledgeable than I. I will just try to not embarrass myself for the next 20 minutes. But first, let me also give you sort of my boom bona fides here. So I'm actually by training a stellar astronomer, a flare astronomer, my thesis was mostly about flares. And so I think we are the #1 transient source in Rubin. We outnumber anything else by sheer number density, but the energy scales are extremely small. So we are the noise that you all have to filter out first to find all the interesting stuff that we've been talking about the last few days. So I feel very at home with these discussions about transients. And let me just conclude my talk as I begin it, which is just to say that LSST and Rubin will make a big impact on SETI. Not only will it make a big, it'll be the tide that lifts all the astrophysical boats that we've been talking about on transients and everything else that, the other science working groups are working on. It will make a big impact on SETI. We, and I mean this we in this room and online, we should work on this. And I believe this community is actually really key to moving these goals forward. And so I'm really happy to talk to you all specifically. I want to talk to all of astronomers about this idea. I want to hear everybody's SETI at home stories. But this community, I think, is key because you all understand how to find the weird and the rare and to deal with all the weird systematics that crop up when you're looking at distortions and transients and things. All the things we've been talking about even just in the last hour are important things that we need to consider when looking for little green men. So you may think about SETI like this. Indeed, we just heard that some people do. This is the famous SETI at home screensaver client. This is the sort of original version from the 90s. This may be your mental model of SETI, right? Doing Fourier transforms of radio data, looking for weird signals, sending it off and hoping that someday ET calls. You may think about SETI like this. I certainly spent a lot of my childhood thinking about it like this. Or you may think about it like this. And fair enough, it's an excellent film. I watched it again recently. It's a great movie. And both, I think, are accurate views of part of what SETI is. Fair enough, both of these are part of SETI. Not the headphones so much. I hope that's been made clear to you all. We don't actually, nobody listens like that with headphones. But these are mainstays of the sort of traditional SETI enterprise, right? This work comes out of a history of radio astronomy primarily, especially in the US and in Russia. And so a lot of the SETI literature and a lot of the thinking is around radio astronomy. And I am not a radio astronomer, and I can answer exactly 0 of your questions about radio astronomy, other than to say that that's a radio telescope. That part I know. I want to help in this talk reset our expectations or reset our views about what SETI is. Part of that is, I think, just kind of taking away the stigma of this area of work, which has gotten so, I think, pigeonholed in terms of funding and in terms of support in this country in the last 30 years for lots of like federal reasons. And as a byproduct, it also has had a really small community working on it. And that's the other reason why it's become very radiocentric, is because the larger community of optical astronomers, for example, hasn't spent a lot of time thinking about this topic. Part of it also is just like good branding that needs to happen. And so this, I think, is one of the smartest things that the community has done in the last decade, which is move from this term, SETI, the search for extraterrestrial intelligence. Every word in that, except for, I guess, search, I have a problem with. And move it towards this term technosignatures, which is meant to invoke this idea of biosignatures, which has become a very popular and very well-funded and supported research area. And really, technosignatures are just an extension of the greater search for life that biosignatures are also involved in, right? These are the same ideas. This is the search for life in some form beyond the Earth. Instead of looking for methane in the atmosphere of a transiting planet, this is looking for some signal which is indicative of technology. I also like that this takes away this notion of intelligence. It takes away some of the notions of our assumptions about why someone might do something or what their intention was, because we don't know, right? We have an example of approximately and possibly less than 1 to go off of. And so we have very hard time guessing what the intentions or the impacts would be from the signals or the signs that we're looking for. So I want to help reset our view of what SETI is. As I view it, SETI comes in a few different forms that we can think about that are applicable to Rubin, or really any data. The first, and again, so the most traditional in our minds, is this search for signals. I'm going to wave my hands in my air quotes and say signals. These are things that are broadcast out with the intention of being noticed, right? They could be like Jodie Foster's signal that was sent from Vega to essentially her with the intention of being noticed. Now, again, the word intention right there tells you that we've got a bunch of like human bias in the equation. We don't know what their intention is. We don't know if they sent it to us or to everyone or only on Tuesdays. We don't know what the intention is, right? But this is one kind of signal that we can and should and traditionally do look for. But there are lots of other things that are technosignatures, that are signals indicative of technology or therefore of an intelligent or technology-faring species. I like to think a lot about lighthouses. I think lighthouses are a really good analogy for what we're looking for. A lighthouse does not exist necessarily for you unless you're a captain. There is a weird signal there. There's this like pulsing light. It has a lot of meaning. Like if you see a lighthouse, it does not mean come towards me. It means go away from me. Don't crash into the shore. That's what lighthouses do if you didn't know. They help you from crashing your boat. But if you didn't know that, if you didn't know the intention that was there, you would just see this periodic blinking source, and you could at least infer that there was some meaning, even if the meaning was opaque to you. Unless you're a bird, in which case or a bat, you just see this blinking light, you're aware of it, but you don't have any understanding of its intention. In this analogy, maybe we are the bats, right? We could be at some lower level of understanding of what the intention is here, and it may just seem unusual. We hope that we are at a level of understanding of the universe and of physics that we're not bats, that we can tell the difference between a natural light source and something with meaning versus a natural light source. But there may be many reasons to broadcast signals into space that have perfectly good meaning, perfectly good reason to them, whoever is sending it, whatever that agent is that's sending it, with the meaning may be totally opaque to us. Similarly, I also like to think a lot about artifacts, right? There are a lot of things that represent civilizations and highly intelligent people that are long gone and whose meanings are only partially understood by us. Okay, these are probably people's homes. This is probably some kind of like public works project with maybe a religious connotation. Other than that, we don't know, I'm not a scholar in either of these areas. I'm waving my hands, but we don't know the details of why and who and how all these things were built. And yet they represent a signal, a sign that intelligent people were here long ago, long after the people were gone. So we can imply that this technology to build these things outlived the civilization. So too may the signatures that we look around other stars long outlive the species that create them. They could create lighthouses that could be solar powered and just go on indefinitely long after they blow themselves out of creation, for example. So that doesn't limit us to just looking, like maybe the Drake equation would suggest, just looking at stars that are young or our age, but these signals that we're looking for could live on essentially forever or throughout the entire galaxy. So I like that the search for extraterrestrial intelligence or technosignatures is taking a much broader view now. This is nothing, I have done nothing here yet. This is all just summing up sort of the state of affairs. There's a really great review from a recent NASA workshop written by Sophia Sheikh here that gives this great sort of flow chart, this diagram of the various axes of merit for developing a technosignature search. There are lots of ways to do this. There are signals which are easy to search for, and those have high merit because we can do the search. This comes into a lot of things that we do with survey science, right? This may not be the best signal, but it's computationally easy and we can do a billion of them, so let's just make the computers do the work, right? We have a lot of signals like that we look for. There are signals you might imagine that are inevitable, waste heat, pollution, things like this that we create that are signals of our quote-unquote intelligence. That if you were looking would be inevitable signals of our civilization, even though they weren't transmitted with the intent to be found, right? So there's lots of ways to rank signals against each other. There are ambiguous signals, things like weird patterns in data, which could have astrophysical origins. They're worth looking for, but they're less compelling, versus unambiguous signals, like you receive a phone call from ET, that's pretty unambiguous. A spaceship lands outside on the quad, that's pretty unambiguous. And the other thing I'm excited about personally, again, I come from this background of stellar astronomy. I think a lot about Rubin in that context. I'm excited that the search for technology, for life, has expanded to other wavelengths, and that there's been a big push to move it beyond just the radio. It's not just radio astronomy, looking at a handful of nearby stars. I think I broke something. There we go, okay. That the SETI community as a whole has moved beyond just radio and has started moving into other wavelength and other time domains. And this is where I get interested and get involved. And I've been very lucky in the last couple of years. My one pandemic success is that I've actually been able to strike up a lot of collaboration with the folks at Breakthrough Listen and the Berkeley SETI Research Center, again, as I mentioned. Now, this is a slide I stole from them, showing some of the instruments that they have time on or they have collaborations with. Again, a lot of radio telescopes, I don't know anything about them other than I can point at them, and they're located in places. NASA's TESS mission I work a lot on because they study lots of stars. The Automated Planet Finder is got a really wonderful high-resolution optical spectrograph. They're expanding their interests and their support for projects beyond just traditional radio SETI, which has been really wonderful. And so this group, which is supported by the Breakthrough Foundation, which is a privately funded institute, has been able to support students and projects in a wide range of astronomy. In fact, this may not be known to many of you, but it is true. SETI is already part of the Rubin community because the Berkeley SETI Research Center, again, funded by the Breakthrough Foundation, has actually bought into, a couple years ago now, the LSST Corporation. And so they are part of the community that is hopefully enabling the science from this great mission that we are all so excited about. The study of technosignatures, like much of what we talked about in the last few days, is the study of outliers. We're looking for things that can't be explained by the normal processes we know them. What I like to tell students is the great thing about working on this area, about working on SETI, is while the likelihood that you're going to find aliens this summer in your project is very low, if you find weird outliers, the likelihood we can write awesome papers about them is 100%, right? So all of our outliers that are really interesting are all like nature papers or all like exotic objects that nobody's ever seen before. And one thing we know for sure about Rubin and other facilities is when you turn on new big telescopes, you can guarantee you will find rare and bizarre and surprising things, right? There's like 100% chance that we'll find crazy stuff in Rubin. They might not be aliens, but we should look just in case they are. Okay, so usually when I give a talk like this, I have to also then introduce LSST. It's this big survey. It has these bands. It goes over a bunch of the sky, blah, blah, blah. You all have seen all this. And then it has these alerts. These things are incredible. 60-second delivery. We already know this. So thank you. I don't have to do any of this setup. You all know what Rubin is. You all have been thinking about this all week. So let's just list the state of affairs we have. We have this giant survey with many types of data. We've got images, we've got alerts, we've got moving objects, which are fascinating. We have big computational resources, right? Software and algorithms are one of the primary outputs of Rubin. It's not just the glass, it's not just the metal, it's all the algorithms that make things happen fast. On the downside, we have kind of wide optical bands, so there are these really wide bands, so we can't really localize what frequency signals might be at. We have relatively long or slow exposures, right, 30 seconds, if you co-add the 15-second exposures, and not that many of them, right, only a few hundred exposures from most stars, so we're talking about an integrated observation of a star of only a few hundred minutes over 10 years. Like, this is not that good of a characterization of any given star, for example. So we need to start thinking about, with this huge étendue, this huge data set, something like 20 billion stars that we're going to observe within our galaxy, what are the kind of signals that we can look for, we can think about? Now, I have a few listed here that I think are interesting, that are kind of general projects that we've been working on with students, but I want to just say right up front, I want to talk to you about this. If you have ideas, if you're scratching your head about this, if you come up with something late at night, please email me, or like, let's collaborate on something, because I think there's a huge amount of parameter space that's wide open, and there's very little literature supporting this yet. And that's one of the exciting things, is we know this is a good idea, at least I think it's a good idea. I will assert that it is a good idea, and I think there's a lot of work that can be done. Okay, so the first is looking for like color outliers, not even just like transient signals, but things with like weird corners of parameter space. So these could be things like Dyson spheres, or megastructures, or things that have like weird mismatches in their luminosity and their parallax, things like that. Dyson spheres are one example. Probably the more realistic example would be looking at it on a color magnitude diagram, so things that would exist in places where they ought not to exist, for example. Those are interesting objects that could be indicative of some sort of like physical, artificial structure. There are enormous numbers of bizarre variable stars. The favorite of mine, because I come from this Kepler and TESS and stars world, is Boyagin's star, this weird, apparently normal F star that decided to just sort of go berserk for a few days and get really dim. And it's probably dust. We still don't know why it did it, and we don't know how many of them there are out there. There's still only really one. Right? Rubin should reveal many of these objects if this is a normal stage of stellar astrophysics. But there was a moment in time when people speculated maybe this was aliens. I'm not saying that it is. I'm saying that this is the byproduct of looking for weird stuff, as you find cool stuff like this. And indeed, already we see in precursor surveys like ZTF and like Assassin, this is the newest version of this one, very strange. I think this is also actually incidentally an F star, this bizarre plot from Assassin. There are lots of stars doing lots of strange things. Stars are really pesky, and they do lots of really strange things. And so there's huge discovery space here of dippers and variables and strange novae that we've never seen that is just waiting to be discovered. And yes, some of it may have some quote-unquote intelligent origin. One of my favorite simple measurements is the long timescale variability we might expect from things like Rubin. So there's a great program by Beatrice Villarroel called VASCO, which is looking for vanishing or appearing sources over a century timescale, century observations. They go back through archival data a century ago and then come up with modern data, and they want to see, are any stars missing, or have any stars popped into existence? And there's lots of reasons why stars go missing, or stars appear to eclipse, or stars pop into existence. Lots of good astrophysics there, but it's a good, simple measurement that we can make. Take the first image from Rubin and the last image from Rubin. Are all the stars going to be there? Are they where they're supposed to be? This is a good thing we can check. I'm not saying it's a compelling extraterrestrial argument. I'm saying it's the kind of thing that we can put the computer to work on, and then we don't have to think about it. Yeah, so we can search for new candidates, and any candidates we have, Rubin will go nice and deep, and we can go check on old candidates. We can go deep and look for anything that didn't disappear, it just got enshrouded in dust or something. And then lastly, while it's a little tangential, is there the laptop? While it's a bit tangential to, maybe it's in my video, to this conference, one of the amazing things that Rubin will do in the first 2 years, right, is completely blow up the field of asteroid research. There will be an enormous increase in the number of asteroids who have their orbits mapped. And from this, we expect, you can debate about what the actual number is. Come on, laptop, you can do it. I think I've broken your laptop. We can debate what the actual number is, but we expect some number, one or a few per year, of interstellar objects. Things like, yeah, here we go, things like Oumuamua. Things with an unusual orbit that come in from outside of our solar system, right? This is like bread and butter for Rubin. We're going to discover these things. And without getting to the specifics or the politics of this object in particular, of Oumuamua in particular, if they are under some sort of piloted motion, if they are moving in some unusual direction, some unnatural direction, if a asteroid takes a right turn in space, we should see that, and that should stand out as a really strong technosignature. I don't think that's what happened with Oumuamua, but if it did happen, Rubin is like the ideal platform to make those kinds of measurements and to do those kinds of models. And so I think this is a really exciting area that I'd love to see more collaboration. Okay. And to reiterate, I think there is an enormous amount of parameter space waiting to be mined here, waiting to be explored. This is an example of the multi-dimensional haystack that Jason Wright and others have calculated. There's something like 9 different dimensions you can imagine in the SETI problem. How long are you looking? What frequencies? What frequency width? How regularly do you sample? How faint is your observations? All these different areas of parameter space. And surveys are expensive. Rubin is huge and is going to do more in survey science, as you all know, than almost any other facility at any wavelength. And so we think, based on round arguments about possible signals you might detect, Rubin should be, this is in log parameter space here, Rubin should be 2-ish orders of magnitude more complete for technosignature research than any of the sort of existing radio surveys to date, if we can find the right signals to search for. So this to me says there is an enormous amount of parameter space just waiting to be mined for you all to think about. So I'm going to conclude with how I started, which is to say that SETI will be a major opportunity for LSST. We will make a big impact with this survey, with Rubin, on this area of astronomy. I think it's a given, just given how Rubin will do everything. We, the people in this room, should work on this. I think it's an important field. It doesn't have to be the thing we all work on all the time, but it's the perfect thing to work on a little bit of our time, to let run in the background like your screensaver. And I think this community is key. And I'd be happy to talk to you about any of these projects and also stellar flares.
Thanks so much, James. We have time for questions for our speaker. So, Graham?
Thanks for a great talk. It's really interesting stuff. You sparked all sorts of thoughts and questions, but maybe I'll just ask one. I forget the name of the star, but the really weird Kepler star.
Boyajian star from Tabitha Boyajian's group.
That's right, yeah. So we had some undergrads in Birmingham using our local telescope to follow that star up, see if they could see any more variation. But really my question is, I'm just curious, partly for that reason, is there a consensus view at all on what's going on with that thing?
Yeah, so every indication is that the variability was due to dust. Right, we had no contemporaneous multicolor or spectral data during the big dips. What we have had now is ongoing monitoring, like you've said, and Tabby and her group have had ongoing monitoring from her facilities as well. I think LCO has even gotten involved in this. And so it continues to have unusual variations that look like they're consistent with dust. So there's a lot of debate about whether is it like a planetary collision or a cometary thing that's in orbit. But yeah, everything looks like it's dust. What's weird is that there is still no detectable infrared excess, so it can't be that much dust. It has to be just the right amount of dust right in our line of sight. What I also will say, if I can, about Boyajian star, what I love about it, not only is it cool and it's rare, it was sitting on disk for years until citizen scientists, until members of the public from Planet Hunters were looking at it and said, what is this? Like, it was not detected, even though the data was there. It was not revealed or understood or even discovered by the professionals. It was discovered by amateurs, enthusiastic amateurs who were visually vetting our data. And it's a good reminder that even though the Kepler data at that point had been extensively studied, for stellar astronomy even, this amazing paper, this amazing object was just sitting there waiting to be realized. It's a good reminder of humility for us who are working on pipelines and algorithms.
Very nice talk, thank you. I was wondering, so we're pretty much, like you're suggesting that we should be pretty much looking for anomalous stuff like light curves or images or everything we can find. So do you maybe have like a particular list of like metrics in mind that would like actually be aimed at like looking for such a signal?
So I've personally been trying to keep like a list of ideas or projects that seem like they're plausible. I think they broadly fall into two categories. You can either classify everything, and whatever's left over and defies all explanation, that's your candidates. And I think we'll do that. I think that is actually a byproduct of what Rubin will do, is try to understand what every object is that it sees and stick it in some kind of bucket that we understand. Or you can propose observations, or you can propose signals that are impossible, that should be physically impossible. And if you detect that, then that is a signal. That's sort of the cheap way to do it. But then you end up, right, like with a lot of assumptions about what that signal is. So if you assume that stars cannot produce Fibonacci sequences of variability, for example, then go look for Fibonacci sequences, and anyone you detect should be of quote-unquote intelligent origin, until we then discover that stars actually produce Fibonacci flares or something, or coronal mass ejections have some unknown physics that we didn't know, and then you become rich and famous for that.
So let me take the last question, and I guess related to that, is there a list of the most expectable technosignatures? Are we looking for Dyson spheres around stars that show an excess in the infrared, or is it more that we should expect optical SETI, like Paul Horowitz was looking at 10 years ago?
For Rubin, there is not. There has been a lot of work in this space for laser SETIs, for spectrographs, in that kind of space, for optical and very rapid measurements from like laser pulses. Veritas is now being used for SETI in this way, looking for rapid flashes. For Rubin, it is early days. We have a few ideas, but we don't have a complete list. So there's a few projects that me and some students have been working on. We need more help, and I mean, I don't know if this is what Fed's about to say, but we do have a Slack channel that people should join and contribute ideas.
Not what I was going to say, but
Okay.
definitely we do have a Slack channel, and we are looking for people to contribute ideas. So you mentioned Veritas just now, right? So what do you think is going to be the role of multi-messenger, like not gravitational waves, but perhaps, neutrinos or something like that in this?
There have been discussions of using things like gravitational waves or neutrinos as carriers of information. I don't know enough physics to tell you how they would actually do that. So I mean, the problem when you're talking about multi-messenger astronomy is right now we have this many signals we're thinking about, and we can't find outliers from one handful of signals. I mean, you can, but it's a very fraught exercise. The FRB community was in this position for a long time. So I don't know. Somebody who knows more physics should answer that. Vishal.
Yeah, I don't think so. I know more physics, but from a SETI side, I can say that wherever this question comes about what is the right way to basically communicate across large distances, you think about the energy consumption of any mechanism. It's much easier to have a high powerful cell phone than actually move a planet up and down to produce a gravitational wave. So I think radio waves or optical lasers are far easier way of communicating than the other mediums, I guess.
Yeah, from a very basic Rubin standpoint, it's very hard to outshine a star. Like, it takes an incredible amount of energy to outshine a star. It's actually much easier to block light from a star, which is why the sort of dippers kind of phenomenon is interesting, because you can launch things that are relatively stable and cheap, and they can block large percentages of light, much easier than you can outshine something in the optical, for example.
Great. Do we have any questions on it? If not, let's thank our speaker as well as the Breakthrough Listen Project for sponsoring tonight's dinner.
That's right. We hope to see you all at dinner.